Can you imagine being weightless? Not feeling the pressure of that chair under you? If you were here, you wouldn't have to imagine. Weightlessness would be a fact of life, as real as you're swinging around the world once every 90 minutes. 17,500 miles an hour, 5 miles a second. Each dot a mile. San Francisco to New York in 10 minutes. Even as the teletypes around the world pick up the news, we wonder what being in orbit is like. We know that the sky is black and the stars are bright and steady. From motion pictures taken through the periscope of a Mercury spacecraft in orbit 100 miles up and shown here at 48 times normal speed, we know that the Earth is blue and green and tan and streaked with white clouds, and that when the clouds break enough, the noonday sun is reflected like a gold coin on the sea 100 miles below us, and the land and the oceans appear as they do on our maps. And that less than 30 minutes after seeing noon below us, we can watch the night rising to meet us over the Indian Ocean. A 90-minute day. And we know about weightlessness. Most of us indirectly, but not all of us. And for a very few of us, not just 13 seconds or so of weightlessness as part of our training as astronauts, but the real thing. This is astronaut Alan Shepard in Freedom 7. Now, watch the strap just below his left shoulder. There. He's weightless, balanced between up and down, as free from the pull of gravity, from G's, as this loose end of his harness strap. What's it like? Here is Shepard's comment.
It's quite a pleasant sensation, particularly so after the accelerations of the booster ride. We find that we have no difficulty in maneuvering ourselves, and all in all, really, at this point, certainly, no difficulty at all.
But as Shepard implied, it isn't all pleasant. This is a centrifuge, a not particularly merry-go-round. And here is astronaut Gus Grissom undergoing what we might, for contrast, call weightness, acceleration-induced high G loading. To help him sustain this high G loading, the sharp increase in body weight during liftoff and re-entry, each astronaut sat for his portrait in plaster to form a mold from which a precisely contoured fiberglass couch could be fashioned, as personalized as his fingerprint. The couch, conforming exactly to the shape of his body, would fully support him, regardless of the acceleration stresses imposed. In the centrifuge rides, these stresses are imposed in a distinct pattern, a profile which parallels and simulates precisely the pattern formed by the sequence of events which takes place in an actual space flight, except, of course, for weightlessness. First, liftoff. The centrifuge starts, simulating the acceleration of the Atlas. BECO, or booster engine cutoff, takes place 2 minutes after liftoff. The escape tower is jettisoned. Altitude, 40 miles. Acceleration stress, 6 Gs. Acceleration stress, more than 7.5 Gs. SECO, sustainer engine cutoff, 100 miles up, 5 minutes after liftoff. The capsule separates from the Atlas, nudged by 3 small posigrade rockets. G loading on the astronaut, 0, weightless. The automatic control system fires jets of gas to stop any unusual rolling, pitching, or yawing. Then the spacecraft is turned 180 degrees, putting the heat shield forward, tilted up 34 degrees. Speed, orbital, 17,500 miles an hour. After 3 orbits, the retro or braking rockets are fired. The spacecraft is slowed by only about 350 miles an hour, but enough to cause it to drop out of orbit. 40 seconds later, the retro pack is... The spacecraft is then placed in the re-entry attitude, 1.5 degrees nose down. It descends gradually for about 8 minutes. It begins to feel the first braking effect of the Earth's atmosphere. Altitude, about 55 miles. Temperature on the heat shield, 3,000 degrees Fahrenheit. Altitude, 25 miles. Speed, nearly 15,000 miles an hour. Deceleration stress, mounting towards 7.5 Gs again, as the spacecraft slows from 17,500 miles an hour at an altitude of 55 miles to 270 miles an hour at an altitude of 12 miles, all in a little over 5 minutes. At just under 4 miles, 21,000 feet, the king or drogue parachute is released. A few seconds later, at 10,000 feet, the main chute opens. Twelve seconds later, the impact bag is freed, and the spacecraft touches down at about 20 miles an hour. G loading returns to the normal earthbound 1 G. The centrifuge stops. The astronaut has learned something of how he should function during each phase of the stress profile. In turn, the scientists learn from their post-exposure interviews about things their instruments can't tell them.
John, you've ridden both sea level and altitude G rides now. Do you really notice any particular effect of the altitude runs as compared to the sea level runs on your breathing?
Well, no, very little. I know we've had some discussion about this in the past, and we have different opinions on that. I happen to be one that just doesn't particularly notice much difference in breathing between sea level and altitude. I seem to use the same breathing patterns, the same straining patterns. I don't notice much difference at all.
I'm very interested in the sustained G runs. Did you notice any change in the difficulty of breathing as the sustained G run progressed?
Well, no, and I was looking for changes, too, just like that, and I didn't seem to notice much difference in it. I hit my G plateau, the 90-second plateau, and set up my breathing pattern, or had it already established before we got there, really. And this seemed to hold pretty much through the run, and I didn't need to vary it any at all. Now, of course, with it being a 90-second plateau, I think the patterns would undoubtedly change if we went to a longer plateau, because you would be becoming more tired, and you would undoubtedly change your position or change your straining pattern to accommodate the tired muscles if you went to a 5-minute run or 10-minute run. But during the 1.5-minute run, as we did today, which is longer than any re-entry we know of, too, really, for G's at these levels, I didn't change my breathing technique at all.
Thanks for the summary, John. I know you got to catch a plane here shortly.
Acceleration and deceleration with time form only one of the profiles met by the astronauts as they train for space. Astronaut Wally Schirra, pressure-suited as he would be for an actual flight, undergoes a 7.5-hour exposure to a simulator profile in which interior temperature, humidity, and barometric pressure are varied with time.
7.5 hours is a long time.
I agree with you on that.
Sitting, there is some hazard with sitting for 7.5 hours, as you know. Did you follow any routine in particular? Did you do as we asked and flex your ankles, move your toes, strain at the calf? gave you?
I felt I had to do that. You do feel cramped, as you say.
You become restless.
This is, of course, quite different than our normal attitude. We'll be on our back, almost in a prone position. I notice, though, that it's easier to move your legs, as I am right now, in a seated condition, because you can just swing your legs. But on your back, you have to lift your legs to flex your muscles. Although your advice to flex them is a darn good tip.
Wally, during this simulated mission, divided into parts for responding to the question, consider first liftoff and the orbital parts of the mission. At that point, all you have to do is just maintain comfort control. Were you able to do that?
The coolant valve settings that we were playing with in orbit sure proved a lot to me, because the intercom system was telling me what my suit inlet temperature was and what the suit outlet was, and looks like I like about 68 to 70 degrees.
Good. Now, the harder part of it, of course, is the reentry phase, where the inner skin walls of the capsule approach 290 degrees Fahrenheit. Then, with this surface that hot, so close to you, inches away, were you able to perceive this temperature?
Only by radiation. I could feel the heat from the panels coming up on my cheeks through the clear section of the visor plate. And this was a very low order of heat, I'd say, like a nice sunny day out on the beach.
It was entirely comfortable.
Oh, yes. I also noticed on my hands, with the black leather surface facing the heat of the capsule wall, that the heat would build up on the black. Yet when I had the silver side toward it, it was very, very comfortable, and it only proves that the reflective qualities of the silver surface is really worth having.
And for yet another kind of profile, we have the procedures trainer, in which, at the option of the instructor, nearly all of the conditions of an actual flight can be simulated, including the unexpected, which each astronaut's reflexes impel him to deal with quickly, calmly, and accurately.
Stand by.
Astronaut Leroy G. Cooper floats in the orbital flight simulator as though he didn't much care if school kept or not. But this is school. The subject, controlling and balancing by means of gentle and delicately timed jets of air, a nastily unstable replica of an uninhibited spacecraft in flight. But this device is a real lady compared to Mastiff. Mastiff, known otherwise as the Multiple Axis Space Test Inertia Facility, designed to throw the astronaut violently into any attitude, conventional or otherwise, that the real spacecraft may assume in space. But like the spacecraft, Mastiff also can be made to behave quite decently by a trained hand. And so with simulators of various kinds of profiles and specialized activity trainers, with sessions in the classroom treating the physics of reaction engines, problems of navigation in space, the science of astronomy, space biology, guidance systems, the mathematics of ballistics, sprucing up and adding to their own prior college training in engineering and the sciences, and with the study of such eminently practical subjects as how to get out of the spacecraft via the emergency route on the water and via the regular route under it. And how to survive in the desert, using the main parachute for shelter and to form a properly Bedouin-like headdress if, by some mischance, the spacecraft should come down on land rather than on water. And with continued flights in high-performance aircraft to keep reaction time short and reflexes accurate. With all of this, the 7 astronauts prepare as a team to challenge space. And throughout the United States stand many thousand times these 7, supporting, building, preparing with them. Here, for example, at NASA's Marshall Space Flight Center, Huntsville, Alabama, were built the Redstone launch vehicles used to boost astronauts Alan Shepard and Gus Grissom on their suborbital flights into history. While 2,000 miles away, near San Diego, California, the Atlas boosters used for the Mercury orbital flights are assembled. Their inner complexity disguised by the shining simplicity of their outer surfaces. The power of the Atlas engines, developing 360,000 pounds of thrust, capable of pushing the Mercury spacecraft fast enough and high enough to inject it into its 17,500 mile an hour, 100 to 160 mile high orbit. Given this power, this speed, this distance, we were also given an upper limit to the weight the vehicle can carry. So the Atlas played a part in determining the size and shape of the astronaut. No more than 5 feet 11 inches tall, no more than 180 pounds, and of his spacecraft. But other things, too, helped to put a fix on the shape of the Mercury spacecraft. For example, 5,000 hours, just short of 2.5 man-years of wind tunnel testing. Would the shape be stable as it re-entered the Earth's atmosphere, or would it tumble? Would it form a well-defined shock wave to carry away some of the friction heat generated by the wind rushing past it at 15,000 miles an hour? A wind that creates enough heat to melt rock to lava, to make it fall like rain. A wind that drives the heat shield to 3,000 degrees Fahrenheit, 1,000 degrees hotter than this. In all, starting 2 years before Project Mercury officially began, 70 model shapes were tested. This one, for example, was unstable, while this one, although more stable, was structurally weak and heavy. This, stable and stronger, reflects consideration of interior requirements and leads logically to this much more familiar shape, in which stability, space, and structure are well met. And then the final shape, topped with a narrow end to carry the antenna and the braking or drogue parachute, and to form a seat for the escape rocket tower. So we have the spacecraft, about 6 feet across at its widest end, the end with the heat shield and braking rockets, and just short of 10 feet tall, not counting the escape tower. Its outside surface is covered with corrugated shingles of nickel cobalt alloy, thinner than a dime, to allow for expansion as they become cherry red hot during the spacecraft's plunge through the atmosphere. Within an inner pressurized vessel of titanium and his full pressure suit. The base of the spacecraft is the heat shield, shaped to protect him during re-entry. He sits supported by a fiberglass couch with his back to the heat shield. He can look out of a rectangular window that slopes down in front of him, while directly in front of him is his instrument panel and a large lens on which the area seen by his periscope is displayed. Just above and left of the lens is an Earth path indicator, constantly showing the astronaut his ground position on a tiny globe and his landing point. Above the Earth path indicator are panel displays telling the astronaut whether the spacecraft is oriented properly and which way to move it if it isn't. With all, he has about the same room as he'd have in the cockpit of a typical fighter plane, enough for himself and perhaps a small boy. With his right hand, the astronaut controls the attitude of the spacecraft, and with his left, he can twist the grip to fire the escape rockets, pulling the spacecraft clear of the booster in an emergency, like this. With the spacecraft high enough for safety, exploding bolts fire and the escape tower pulls free. Then the small drogue chute is released to slow and stabilize the spacecraft's descent. Then the much larger main parachute streams out. At first reefed to slow the descent further and lessen the shock of the chute's opening full. A test for stitching together with thousands of others to form the fabric of safety and protection, so basic to Mercury planning. For example, the escape rocket in an earlier test. With the elements rigidly held for study. And the 3 small posigrade rockets mounted between the larger braking rockets in the retro pack and used to separate the spacecraft from the Atlas. And another to check out the all-important retro rocket, and the exploding bolts to release the bands holding the retro pack against the heat shield, freeing the pack to drop away after use. And a test of the heat shield itself. And the landing or impact bag folded between the heat shield and the base of the spacecraft during flight, then freed at 10,000 feet as the main chute streams to soften the impact of landing. Then the flight tests. The Little Joe series from Wallops Island, Virginia, testing spacecraft performance and the escape system. And Big Joe for a 15,000-mile-an-hour check on the behavior of the spacecraft at high speed. And particularly of the heat shield during re-entry. And Ham, our first astro chimp, blazing the Redstone suborbital trail for Alan Shepard and the flight of Freedom 7. Looked at mechanically and analytically, the flight of Alan Shepard on the morning of May 5th, 1961, could be described as a test to check the performance of the early design, round-windowed spacecraft in ballistic flight. Just as Gus Grissom's trip, 2.5 months later, could be considered a test to qualify the final rectangular windowed and otherwise matured spacecraft under the same or similar flight conditions. Mechanically and analytically, yes. But do you feel as though you were watching just another flight test?
Command, 30, what?
Oh, Roger. Periscope has retracted.
That's confirmed periscope pickup.
Main bus 24 volts, 26 amps.
15. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
Oh, Roger. Liftoff and the clock has started.
And it had.
Yes, sir. Reading you loud and clear.
Not only for Shepard and Freedom 7, climbing the clear, bright air above Cape Canaveral for the airless space beyond. Not only for the recovery forces, now rallying at the predicted impact point to pluck him and his spacecraft from the sea, but for the United States manned spaceflight program as well. A test? Yes. Of a man, a machine, a system, a program, and a nation. The clock carefully built, carefully set, had indeed started. But care didn't stop with the starting of the clock, any more than training or teamwork or testing did. Sheathed in plastic, the spacecraft arrives at Cape Canaveral. Workmen assemble each spacecraft, taking every possible precaution against contaminating it with dust or metal particles that could cause a failure. The fiberglass contoured couch is installed. The retro rockets are checked. The Atlas is carried on a special trailer to pad 14. And then is slowly and carefully raised to its position in the gantry. A plastic sheet protects the upper surface of the adapter, which forms the topmost section of the Atlas and provides the seat for the base of the spacecraft. Then the spacecraft for mating with the Atlas. The adapter is checked for the last time, and then the spacecraft is cautiously lifted to the 11th level, swung gently in above the adapter, and then lowered into position. Then finally, the escape tower, hoisted and placed. Care, and from care, assurance and calm. John Glenn, neither more nor less outstanding than Carpenter, his backup man, than Cooper or Grissom, or Schirra or Shepard or Slayton. Rather thrust into singular distinction, at least in part, by the simple arithmetic fact that out of 7, only 1 can be first to orbit.
We'd had our holds, of course, on previous launch attempts. We were asked how the delays affected our readiness. I think Scott Carpenter put it in probably the best light when he said I was the most fortunate one around with all this excitement going on, because all I had to do was sit back and just hone the edge a little more and keep in good shape. tape switch off. Now, steer on. CO, verify the following: instrument panel camera, pilot camera, and tape recorder. Tape recorder is running. Panel camera is running. The day on the 20th, though, that morning, as the weather started to clear and we could see the big blue holes coming up, I really felt that we were in a go condition at that time because the booster was ready and everyone, I think, sort of gets go fever when you get all conditions set right. I think everyone was excited that morning. Anything I can show? Fan leader. Go ahead. Verify all tapes have been removed. All tapes have been removed from the adapter. Can you find out if they want to have the television cameras covered up? Oh, the camera, everything is disconnected. No, I haven't been disconnected either. Still on TV. Leave it all, fella. High pressurization. A couple of good bumps there. Roger. Water systems are coming on. You'll probably hear them. Roger. Looks good, old man. Boy, can you imagine? Here we go. Now, back to one.
To the east and around the world, the Mercury Tracking Network. Bermuda, the Mid-Atlantic Ship, Gran Canary Island, Kano, Nigeria, Zanzibar, and the Indian Ocean Ship. Mouchet, near Perth in Western Australia. Woomera in the bleak Australian desert. Canton Island in the mid-Pacific. The Hawaiian Station on the island of Kauai. Point Arguello in California. Guaymas, Mexico. Plus radars at White Sands, New Mexico, Corpus Christi, Texas, and Eglin Air Force Base, Florida. All feeding information to the computers at Goddard Space Flight Center in Greenbelt, Maryland, where it is processed and in seconds passed to the Mercury Control Center at Cape Canaveral, Florida. Through this network, we can talk to the astronaut, and we can track the path of a spacecraft, watching for this scope display as the spacecraft comes over the horizon, seeing it on radar, first at long range, 700 miles, then locating it within a half a degree at a distance of 500 miles. Each station teletypes the radar information to the computers at Goddard Space Flight Center, where the spacecraft's exact orbit is determined. Through the network, we can collect some 100 items of information on the physical condition of the astronaut and the spacecraft. We can monitor his pulse, his respiration, the G-loading on man and spacecraft. We can determine, seconds after the spacecraft separates from the Atlas and turns heat shield forward, whether its orbit is good or whether it should be brought down. And we can determine, as re-entry starts, where the spacecraft is going to land, and can bring it back to Earth at any time if the situation warrants.
Very good. Missile alarm, 1 minute, 15 seconds. Missile power, go. RF systems, go. Propulsion, go. AMR, go. Telemetry quality, go. Mercury capsule, go. 7 from Cape, how do you read? You Roger, loud and clear. How many? -40. Status check, pressurization. Lock's taking. Have a blinking high level light. You are go. Motor systems. Retract now. Range operations. Roger. Mercury capsule. Go. All pre-start panel lights are correct. The ready light is on. Eject Mercury umbilical. Godspeed, John Glenn. 5, 4, 3, 2, 1, 0. Roger, the clock is operating. We're underway. You're loud and clear. Roger, we're programming and roll okay. A little bumpy along about here. Roger. Stand by for
minute. Fuel 102, 101, oxygen 78, 100, amps 27. Roger, loud and clear, flight path is good, 69. Roger, check's okay. Mine was 70 on your mark. Have some vibration area coming up here now. Roger, reading you loud and clear. Roger, coming into IQ a little bit. That little contrail went by the window or something there. Roger. Fuel 102, 101, oxygen 78 to 101, amps 24, still okay. We're smoothing out some now, getting out of the vibration area. Roger, you through Max Q, flight path is... Roger, feels good through Max Q and smoothing out real fine. Sky looking very dark outside. Cabin pressure is holding at 6-1, okay. Roger, cabin pressure holding at 6-1. Roger, I've had some oscillations, but they seem to be damping out okay now. Coming up on 2 minutes. They're building to 6. Roger, reading you loud and clear. Flight path looks good. Pitch 25, stand by for... Roger, Pico. Back to 1 1/4, the tower fired. Could not see the tower go. I saw the smoke go by the window. Yeah, we confirm staging on DM. Roger. There the tower went right then. Have the tower in sight way out. Could see the tower go. Edison Tower is green. Roger. 1.5 Gs. Friendship 7, Bermuda has you. Roger, Bermuda, stand by. This is Friendship 7. All Roger, reading you loud and clear, 7. Cape is go. We're standing by for you. Roger, Cape is go and I am go. Capsule is in good shape. Roger, 20 seconds to Seco. Roger. Indicating 6 Gs. Seco. Posigrade's fired, okay. Roger, stand. Roger, 0 G, and I feel fine. Capsule is turning around. Oh, that view is tremendous. Roger, turn has started. Roger, capsule turning around, and I could see the booster during turnaround just a couple of 100 yards behind me. It was beautiful. Roger, 7. You have a go. At least 7 orbits. Roger, understand go for at least 7 orbits.
And now John Glenn is waking, orbiting very nearly due east, away from the United States coast. 5 miles farther at the tick of every second.
Roger, Friendship 7. I am taking xylose pill now. Roger, Friendship 7, understand.
Across Africa, then watching the sunset over the Indian Ocean.
Roger, this is Friendship 7. I can see the dark side coming up in the periscope back behind me at present time. That was sure a short day. Say again, Friendship 7? That was about the shortest day I've ever run into. Time passes rapidly, huh? Yes, sir.
In the night, over Australia, then the sun rising behind him as he crosses the Central Pacific.
This is Friendship 7. I'll try to describe what I'm in here. I'm in a big mass of some very small particles that are brilliantly lit up like they're luminescent.
Then across the United States toward Cape Canaveral. Once around. 45 minutes of night and 45 minutes of day.
Little or nothing of zodiacal light at the moment. Friendship 7, the sun is going down again now. Coming off automatic in yaw, and yawing a little bit to the left, observe it. Flying with yaw handle pulled.
During the flight, the automatic stabilization and control system was causing some difficulty. Didn't appear to be correcting the way it should. Was able to use the manual control and just didn't cause any trouble at all. It seemed very natural after all of the trainer work we've done. Trainer simulations, incidentally, were very, very close to the orbital control situation. When we started having this problem at the end of the first orbit, I was largely on manual control from there on till the end of the flight.
5, 4, 3, 2, 1. like I'm going back toward Hawaii. Roger, fire retro light is green. Roger. Roger, retros have stopped. Hunter? Keep your retro pack on until you pass Texas. That's affirmative. Shot. I'll tell you, there's no doubt about it when the retros fire. Yeah, it has with your comments.
The ground telemetry receivers had picked up an impulse that we possibly had a loose heat shield. And for that reason, it was deemed advisable to keep the retro package in place during re-entry so that it would go ahead and burn off, but by that time we would be in a high enough aerodynamic force field to keep the heat shield in place in case it was in fact loose.
This is Texas Capcom Section 7. We are recommending that you leave the retro package on through the entire re-entry. This means that you will have to override the 05G switch, which is expected to occur at 0443. This also means that you will have to manually retract the scope. Do you read?
This is Friendship 7. What is the reason for this? Do you have any reason? Over?
Not at this time. This is the judgment of Cape Flight.
Roger. Say again your instructions, please. Over.
I didn't really contest this decision from the control center because I knew that the experts we had on the ground had certainly thought this thing out much more thoroughly than I could in flight. I knew that there would not be any change of this magnitude made unless it had certainly been considered from every possible angle by many, many experts on the ground, all the people that designed the system and all the other experts that were in the control center.
Roger, understand. I will have to make a manual 05G entry when it occurs and bring the scope in manually. Is that affirmed?
That is affirmative. Friendship 7.
Roger. This is Friendship 7 going to re-entry attitude then in that case.
Friendship 7, Cape Flight will give you the reasons for this action when you're in view.
Friendship 7, this is Cape, over. Go ahead, Cape, Friend 7.
I recommend you go to re-entry attitude and retract the scope manually at this time.
Roger, retracting scope manually.
While you're doing that, we are not sure which one you're running with the retro package on. We see no difficulty at this time in that part of re-entry. Over.
Roger. Understand.
The spacecraft descends gradually toward the top of the atmosphere under the increasingly insistent pull of gravity.
Friendship 7.
Stand by.
This is Friendship 7 going to fly by wire. I'm down to about 15% on manual.
All right, you're going to fly by wire for a and we recommend you do the best you can to keep a zero angle during re-entry. Over.
Roger, Friendship 7.
The spacecraft begins to pile up a shock wave. Speed, 15,000 miles an hour. The temperature of the heat shield is approaching 3,000 degrees. Its fiberglass surface is beginning to ablate, to char, to melt and vaporize, streaming away to form a glowing electrically charged wake.
Go ahead, Cape. You're going out.
We recommend that you...
Radio and telemetry contact falters, stops, blocked by the cloud of charged air.
This is Friendship 7. I think the pack just let go.
The straps on the retro pack broke loose, and I felt a bump on the capsule and thought that the retro package had jettisoned as it was supposed to do. Apparently this was not true, but I thought so at the time.
This is Friendship 7, a real fireball outside.
This made a pretty spectacular re-entry from the capsule standpoint, because as it went on into the higher heat pulse in, and this glow picked up outside the capsule to sort of a bright orange outside the window, it became apparent that something was tearing up on the heat shield end of the capsule, because there were large pieces from anywhere from pieces as big as the end of your finger to pieces probably 7 or 8 inches in diameter, were breaking off and falling off the edge of the capsule and coming back up too brightly. You could see the fire and the glow as they would come back up past the window. This obviously was the retro package tearing up and breaking off as we knew it would if it had been retained. I thought at that time, however, that the retro package had already been jettisoned. So there were some moments of doubt there as to whether the heat shield had been damaged and whether it might be tearing up itself. And this could have been a bad day all the way around if that had been the case. But it was very spectacular looking out into this orange glow outside the window, bright orange glow, and seeing these big flaming chunks go back along the flight path.
Zero 0450. Okay, we're through the peak G now. 7 so close into the set. Over. Friendship 7. Drogue is out. Roger, is the drogue holding on? Roger, drogue looks good. Roger. Scope did not come out. Checklist. Roger, pumping the scope out. Left over. Say again. Roger, re-entry checklist complete. Standing by for main at 10. Roger. Coming down on 10, snorkels are open. Roger, understand, snorkels open. Roger. Main chute is on green. Chute is out in reef condition at 10,800 feet and beautiful chute. Chute looks good. On O2 emergency and the chute looks very good. The rate of descent has gone to about 4.2 feet per second. The chute looks very good. Hello, Mercury Recovery. This is Friendship 7. Do you receive? Mercury, Friendship 7, this is Steelhead. Loud and clear, over. Roger, that's affirmative. Descent is normal, indicating 40 feet per second. Friendship 7, this is Steelhead. Be advised, I have you visually... Roger, what is your estimate on recovery time, over? Estimate pickup now at 20 minutes, over. Roger, understand. 20 minutes to pickup. Landing bag is on green. Friendship 7, ready for impact, almost down. Here we go. Friendship 7, this is Steelhead. Hold you in the water. What is your condition, over? Roger, my condition okay. Does the capsule look like it's okay, over? Friendship 7, reference your last affirmative. Capsule looks good from here, over. Roger, understand they want me to stay in the capsule until rescue. Friendship 7, Steelhead, that's Charlie, over. Roger.
And so it ends. Our first manned orbital flight, with John Glenn receiving congratulations from the President of the United States. But in ending, it forms a new beginning. A beginning not only to the line of Project Mercury orbital flights, but to a series of ever higher, ever longer steps. More training, more teamwork, more tests. For after Atlas, Saturn. after Mercury, the two-man Gemini for Earth orbits of a week or more. And then Apollo, a three-man spacecraft. And with it, flights first around the moon, then to the moon, landing and return. Then ultimately, flights to other planets. For the placing of Americans on the moon is not an end in itself, but rather the focus for development of the national resources needed for adequate space science and exploration. Through the lunar landing program, we give strong stimulus to science and technology to produce the competence needed by the nation to meet the great challenges of our age, here on Earth and beyond the Earth, in space.